case of vector field visualization to the more advanced techniques used to visualize tensor fields. Before getting into details, I would like to show a couple of videos summarizing the effective use of several visualization techniques that we studied in the previous weeks and how they can be combined to provide effective visualization of interesting use cases in the, for example, the Hurricane Katrina simulations. Here we have multiple ice surfaces with transparencies and color maps. Here a case where also we have volume rendering showing this same transparent features and the rotation, but then more explicit information provided by the streamlines showing the core of the rotation. Obviously here the vertical dimension has been highly exaggerated. And in a more advanced visualization, nicely choreographed, here we see how high quality volume rendering can show the structures of the clouds, and then a carefully mixed set of streamlines show the direction of the flow and the rotational structure inside the hurricane. This is clearly the type of visualizations that have a very high value because this is a perspective that a scientist cannot take out of data directly, and so can only be accomplished with simulations and visualization carefully chosen in interesting locations. So going to the challenge of visualizing tensor fields, we first have to look at what a tensor field is. So we'll look at so far at scalar values. So those are zero dimensionals, they're just one value per location, one dimensional vectors per location, and tensor becomes at least two dimensional matrices. And so quickly one can see how in the case of the scalar one can just have a single value that can be mapped, for example, to color, kind of fairly intuitive. Vectors still have a geometric interpretation. You can think about an arrow in a particular location with the direction and magnitude. Still, already we have seen how much more difficult it is to show many of them at the same time. For tensors, really the challenge is that the mathematic representation doesn't give quickly rise to an intuition, right? So here we have the single numbers, arrows and vectors. Here it's just a matrix, and it's really hard to intuitively understand in a direct way. Kind of a little bit more formally, those are the distinctions. And again, we see that how once you start going into at least a two-dimensional matrix, it's very hard to think of that other than as a matrix and not just as an intuition for a geometric object. So trying to understand better what they mean, one can think of the case of mechanical engineering and stress tensors, where the 2D or in this case three-dimensional array of the stress tensor shows the deformation, the preferential direction of the deformation for an object in different directions. So if the 3D array of numbers is not symmetric, under similar forces would lead to an object that, for example, could deform in an asymmetric way. And so that's a way of thinking of a stress tensor. Here a little bit more intuitively and more in detail in a local region. You can think about having a local position where there are two point of pressure, and here we see how the pressure propagates inside this three-dimensional brick. Those are the direction of propagation, but then you have transversally the surface of the um, direction that could apply to transversal deformation as well. So here we can see an alternative way of looking at the same type of information. Here, those are the two locations of pressure and how that kind of flows in those directions inside of the body. And again, transversally, we see the deformation that is not flat, but depends on the pressure that is being put on the top of the three-dimensional cube. More interesting views into this type of data, location of pressure, evolution of this pressure inside the body, and kind of looking at things from a side view, again, to give an intuition. But at the end of the day, one has to understand from the application perspective what for example, the stress tensor is. Another application case where, for example, would be a tensor that represent electrical magnetic field. This is kind of the Fulmer representation, and this is the various surface of preferential direction. And again, this can be somewhat intuitive if one has a sufficient understanding of electromagnetism. For example, fortunately, I have also a degree on electrical engineering, so this actually seems fairly intuitive, but I realized that without any background, this might actually be hard to absorb. In the medical space, there are very interesting cases of fiber tracks that are here. They show preferential direction of diffusion of water molecules, and those can be kind of visually represented in an intuitive way. In terms of actual data, they are acquired through technique called diffusion tensor imaging, and it's a technique that kind of similarly to CT and MRI scan give a scan in this case of a brain, but instead of giving you a say single value like a CT, kind of a density value per location, for each location one would have a full-blown tensor, and here would be kind of a 2D projection of that, and that would show preferential direction of transfer, for example, of water molecules into the brain. And so this type of modality can give rise of very interesting visualizations. Here we see those tracks where we look at the preferential directions of the primary direction of diffusion. Notice that one has to remain aware, again, knowing the application, that those are not the only direction. Those are the preferred direction. There is still diffusion in all possible directions, but those are the one with greater favor. So those, even if visually may look similar to a streamline, practically they have a very different meaning. Obviously, depending on the different strength of the different preferential direction, that may be more or less true. Just to have a kind of very simple, intuitive understanding of how this works. If you think about making a droplet of liquid, for example, here on a Kleenex, if the diffusion from the droplet happens in all the direction more or less uniformly, it means that the 2D array of the diffusion tensor it's symmetric, and the two main preferential directions have the same intensity. If we have a different type of paper, like a newspaper, and then the ink distributes more along one axis than the other, it's like having this ellipsoidal structure where the two main directions, one is kind of longer than the other. And so in going back to the medical case, this would be the direction of the fiber tracks. And so one can use this type of ellipsis metaphor to indicate diffusion that is completely isotropic and can go in any direction with no particular preference, to diffusion can happen very strongly in one direction and de-emphasizing in the other direction. And so an obvious way to go about it is actually to visualize the diffusion through ellipsoids where the shape of the ellipsoid can express those directions. Those could be this would be the total isotropic. One could have two equal direction and one smaller one, so this is kind of isotropic in the plane but highly anisotropic in the normal direction, or being strongly in one direction. In this case you have this kind of ellipsoid structure that is highly deformed along one axis. And so here it's in a case where one visualizes this anisotropy in the case of white matter tracks, where since for every location one will have a 3x3 array in those images, you can see that that can be shown as an array, 3x3 array of images, where the same point in that particular location has those values that we see in an array. And so for a different location here in the middle, though this is the array of numbers, and then you have a 3x3 map of the location of that. And so on and so forth. So one can do, as one can do also for vector, a component by component representation, although one could not go much beyond a 3x3 array, otherwise the number of visualization grows too much. Another application still in medicine, but kind of very different in nature, is when here we go back to the idea of stress. And for example, if we build an implant, we want to see how much is the stress and how well that will kind of be maintained over time. And then the future, the stress tensor visualization can help understanding how stable and how much one would expect the implant to kind of behave well over time. So visualizing the tensor and looking at a particular location of a higher stress. So here, for example, where two bones are in contact with each other, can be a good indication of the fact that one may have to reshape the implant so that the stress is kind of as low as possible and well distributed throughout the surface. Now, looking at some of the mathematics behind the tensor field, the good news is kind of we already discussed this a little bit for the derivative of vector fields. So one can look at diagonal forms of the tensor, and in particular you looking at eigenvector and eigenvalues as a way to build basis for those tensors. So in particular, in this case, you have lambda 1, lambda 2, lambda 3 are the three eigenvalues for this 3x3 tensor, and those can be useful for building singular value decomposition or principal component analysis. And so what the ellipsoids that we talked about before, effectively we can think about the difference, kind of the ratio between the different eigenvalue represent the structure of these ellipsoids, namely if the three eigenvalues are the same in magnitude, we have this spherical structure. If two are equal and say one is much smaller, you get this planar structure. And if one is much bigger than the other two, you have this kind of linear structure as well. So there is kind of a little bit of a intuitive representation. In terms of computation, this is something that we've seen, so I would refer you to the previous classes. I'll just go through quickly. The computation of the eigenvectors is the solution of this characteristic equation of the matrix. And so the determinant of A minus lambda I equals 0 is what will allow us to find all the different values of lambda. And then correspondingly, we find that the eigenvectors are the vectors for which A times x is the same as lambda x, which means, as we saw, that multiply the vector by a scalar, the same as the multiply the vectors by the array. And so is the situation where we saw the vector multiplied by the matrix, instead of being applied into a rotation, is simply scaled along this particular direction. Again, please look back at the vector field representation for a reminder of how this works, and we had a little bit of a demo to give an intuition on how that works in practice. This is a very simple 2x2 example to see how this expression can be solved, and in fact how that could be written kind of in closed form. Obviously, this is not true. You don't have a good form like this for the higher order cases. And so this goes back to the geometric intuition. In particular, so when you multiply a vector by the matrix, and the result goes from the original direction to another direction, that's the most common case, unless the vector is an eigenvector, in which case this direction are aligned. And those are obviously the important directions in the tensor field. Now, how that maps to visualizing tensor field, and how easy or hard it is to visualize such a field. Clearly, tensor fields are much more challenging than vector or even scalar. There is kind of really a limited intuition in how they be represented. Obviously, we have to visualize only part of the information. For example, what are the directions, but not the actual value. They are multivariate in nature, so that makes things really hard. And because of this presence of multiple pieces of information at the same time, the more you try to visualize all those things at the same time, the more you have clutter and occlusion, and then you can visualize only few numerically, so a few elements with lots of information, or many but with reduced information content. Certainly, knowing the application domain can be a huge help. One can look at things kind of in a very direct way, with various type of glyphs or illumination, and look at hyper streamlines as a way to visualize them. And in the later module, we'll see also how to generalize the line integral convolution techniques and texture based techniques for this type of application. So in terms of direct visualization, we already saw a little bit how For example, for a 3x3 array, one can visualize component by component and have multiple images. And of course, one will have to correlate the different numbers to get a sense of the full um, tensor structure. One can also derive the scalar properties out of the tensors. For example, the magnitude is an important component. The trace, it's another component. And so those could be being scalars, then can be mapped into simple numbers that can in turn be visualized as through color maps. And so here, for example, we look at in a divergence, a curl in a vector field. Those could be mapped also to having pseudo colors on a tensor field. And so here you can think about a color sphere, so where different directions have different colors, and that's going to be mapped into the visualization of the on this particular brain model. And so the different colors can show how the flow is anisotropic in different direction, and I guess the gray area is where that's the most isotropic. So it can be somewhat intuitive in terms of being isotropic or not so much intuitive in terms of realizing, oh, green means you go bottom left and blue top right, but still can be very useful. So here is showing more in detail this idea. So here we have a kind of the sphere of colors with respect of the first eigenvector. And then now, instead of having the typical vertical color map, our color map, it's a little guidance sphere. And then here we see in the visualization the different parts of this brain model, how the flow is anisotropic in different directions. So here, for example, we see the red is kind of horizontal in direction, so this entire area has flow that follow that particular direction. Here we see how different parts are different directional flow, but here it's kind of the green part is vertical flow and the red part is horizontal. So here we start seeing some kind of interesting clusters of flow in particular directions. Now, going back to representation with effectively three-dimensional glyphs, one can represent second order symmetric tensors as ellipsoid, as we have seen. And so here is the case of having a slice of a 3D volume, and the glyphs of those ellipsoids kind of show the preferential direction along this particular plane cross sections in 3D. So the normalization of the ellipsoids can allow to pack more information together and focus more on the overall flow direction and less in local intensity. And here we can see how this clustering of flows in different directions effectively mimics brush strokes for a tensor field visualization. And so here we see in some area things are a little more consistent, in some area they're a little bit less and can distribute in different way. Here they're larger intensity and kind of then visualize in a more sparse way. So another image of this particular technique, so where one can show different visualization and then overlap one with the other with a different coloring, the size of the voxels, and the direction of the tensors. and the visualization that results in a combined representation of those aspects. Some of those were visualized on slices. One can do also everything in full 3D. And these ellipsoid structures, they're still sufficiently visible even if they are relatively small. And so one can appreciate their distribution in space and their relative structures. And then there has been different techniques where those shapes have been taken, either ellipsoids or more box structures, and the effects, while they show somewhat similar information, there is for example, one can make the case that with these box models, when they start aligning with each other, the coherence of the flow is, the preferential flow is kind of much more highlighted. And when things are kind of not coherent, things it's better understood compared to the shape of the ellipsoids. So the diffusion tensor can take advantage, obviously, from a combination of different techniques. And in fact, it's very important to do multiple visualization that concurrently show the same type of information. Here we see different visualizations where we see the preferential direction of the tracks, a combination of glyphs on a particular slice, or in 3D, both the flow of the main directions and a set of the glyphs kind of more in the background. In all these cases, it's very important that the user understand which subset of the data is being highlighted and which subset of the data is kind of hidden, is not visualized, to avoid cluttering. Practically, it's the range of shapes. It's key to have an expressive visualization. And so here we see the different degrees of isotropy or anisotropy. And so you can think of having different type of ratios between the eigenvectors and how those can give rise to different shapes. And so even the basic set of elements that give us the key in the visualization need to be properly visualized. And so this is kind of the equivalent of a simple color map for a scalar field visualization. This is instead the key for a tensor field visualization itself. And so you can see that there is a major challenge in how the human visual system can or cannot properly identify the shapes. And in particular, that's influenced from the visualization viewpoint, right? If we have an ellipsoid from a different viewpoints, even if the shape is the same, it may be identified in different way from a visual perspective. And that's where, as we saw, using other shapes other than ellipsoid may favor a better recognition of the shapes in context in 3 dimensions. So this cuboid represent similarly the the different ratios between the eigenvectors. And so instead of a sphere, we have a cube, and then the cube could become a very elongated parallelepiped or more of a thin square. And so those are much easier to recognize even if they're being shown from different viewpoints. Similarly, there is opportunity using cylinder structures, and so each of those techniques has advantages and disadvantages like lack of symmetry versus easy to represent the information expected more directly. So there are techniques that try and combine advantages and disadvantages of those different techniques. The work from Gordon Kindleman using super quadrics aims at achieving this goal with the sophisticated use of shapes based on super quadrics, where those are neither simple cylinders nor simple parallelepiped, but are shapes that preserve fairly well and they're identified fairly well in terms of representing the preferential direction of a tensor. Even more advanced approaches try to highlight some of the preferential direction even more, and so that one can have this kind of spike structures versus more flat models, so that the user can get an intuitive view of where the flow direction moves. And so this is kind of how one can think about this super quadrics, where the advantages of the different techniques can be blended with these single parameters and achieve a different group of elements depending on the blending factors that we can see here at the bottom, and allow to select more carefully the output they want to achieve. As any advanced techniques, there is the upside of having a more sophisticated way of choosing the shapes, and the then downside of having a large set of parameters and the difficulty of making those choices. So here though, going back to the comparison, is that the simple ellipsoids are more subject to hard way of perceiving the shape, while the super quadrics are much easier to recognize, even if they are being visualized from a odd angle. And so generally from a perspective of the user intuition and providing accurate information, they tend to be a more powerful paradigm. This is a direct comparison of the same information shown through traditional ellipsoids. So here you see, for example, how we see just the simple tips, how here the flow is not quite as well highlighted, and how instead this information is much better summarized and expressed in the visualization here with a super quadric approach. Now, for different tensors, the different type of glyphs may be more advantageous. Here, more use of the super quadrics approach, and here going to the glyphs with this additional parameter to highlight particular spiking directions and how they can be used in practice to highlight these particular regions. Again, this is the use of those could be preferred or not, depending on the application and depending how important it is to highlight those particular directions. The opacity is also an aspect that can be used in highlighting different parts of the visualization process. And so one can look at how to use opacity. So here we talk about barycentric opacity in the sense that we look at the opacity as assigned to the three corner of the triangle, and then looking at the blending between the three, so the barycentric coordinates of the value, and then using the opacity to highlight or not. So when things are transparent, different regions in the data sets, and that's a nice way to, as you can see on the right, to highlight different part of the data. Even though the visualization techniques is the same, it highlights different regions inside the data based on their different directions. Also, lighting is an important aspect, as we've seen in different examples. And here, more in detail, we look at how the sphere of all possible directions can encode the direction of the preferential flow, and that's mapped directly into the visualization itself, into the in this particular brain data set. So the lighting can improve and highlight more different directions. So from the basic visualization that we saw before, you can have these lit tensors where you have a stronger sense of direction because of the lighting conditions. And so here we can see how that maps to visualizing a particular data set. And then this is with the coloring and lighting that improve the visualization. So glyphs, as we have seen, can be useful. We discussed the use of glyph also already for vector fields. The basic considerations remain the same, that the more we make a particular glyph complex, showing, for example, twisting direction, rotation, and different property, makes the glyphs more informative but more complex, and so only a few of them can be shown at the same time. This is a particular use of glyphs along certain directions into the data, and as long as they're used in the sparse way, that can be very effective in visualizing a set of property into the data. Obviously, you can imagine how having a densely packed set of glyphs of this type would make it hard or effectively impossible to appreciate the different values that are being packed into the glyphs that is being shown. And last example is the very complex glyphs for a wave propagation. So here you can see how you have this very complex shape with coloring on top and so on. This is a type of glyph that really one can show just a handful in a visualization. As part of the research, lots of techniques try to develop a more sophisticated way of packing information and still being intuitive. Now, if you think about this as a fourth order tensor, it's still relatively intuitive instead of looking at the list of numbers. Still very hard to visualize, especially if one had to have several of those visualized concurrently on the screen. And this concludes this first module. And in the following one, we'll focus on texture-based techniques, again, for visualizing tensor fields.